Hello and welcome to a new series that I am tentatively calling Toy Chemistry. I might change that name later, I'm not sure. This is based on a paper that came out in Physical Review Letters recently. That is, the paper itself is a follow-up to a pretty revolutionary paper a few years ago that looked at this topic of self-organizing chemicals. Or self-organizing chemical structures, I guess I should say, in sort of thermodynamically driven systems, which is a fancy way of saying how possible is it for life to assemble itself through mechanical processes. Basically, the conclusion of the original paper a few years ago was that life is not some fluke that happens on planet Earth, but that it's kind of an inevitability of the laws of thermodynamics. I'm grossly summarizing here, but that's how I read it. That's how I read that original paper. And the authors have recently come out with an update just this past summer involving a computer simulation to demonstrate this process. And I've read through the paper, and it seems like the underlying physics it opens up with this probability stuff that I'm still trying to wrap my head around. I mean, I understand this stuff in general. I'm just not entirely sure of where it comes from. But the underlying physics that they get into in their second page here is all pretty straightforward. They're simulating a series of particles whose coordinates are given by xi here. Those particles are subjected to a few forces. First, they're all subject to an external harmonic oscillator potential. So that's this negative K0 xi here. So they're all confined to a well. One of them, the zeroth particle, is subjected to an external driving force. So this is basically the external force that is causing them to self-organize. They're subjected to a damping force, pretty standard, and then they're subjected to spring-like forces between each other. So these are the bonds between individual particles, except that not all particles are bonded. So that's what this Lij matrix is here. It tells you whether a given pair of particles is bonded or not. So if you like, it's from what I am picturing it as is a matrix of ones and zeros that flip between ones and zeros based on whether they are bound or not. The bonding is governed by this potential here, where you've got an unbound state on the left, a bound state on the right, and in order to go from bound to unbound or vice versa, basically to establish a bond or break a bond, you've got to overcome this potential barrier here, this B of delta X. And so they did this in one dimension, so you imagine you've got all these particles oscillating here. They draw the little connections between them here as to represent the bonds, and then they make these network diagrams, these graphs here in Figure 1c that shows how the bonds are arranged. And of course, it's a randomized process, so they get all sorts of different configurations out. And what they were looking for, if I understand correctly, was common features in the bondings. In other words, if you have sort of randomized initial conditions and randomized establishing and breaking of bonds, what kind of overarching structure do you get at the end? And they found these neat resonance patterns. I'll let you find the paper. It's in Physical Review Letters. Very exciting stuff. What I wanted to do to help myself understand what's going on here is to make a sort of simplified version of this. I don't know how far I'll be able to take it, and I certainly don't expect to be able to recreate their results. They made simulations of 20 particles, which of course is going to take oodles and oodles of computer time, as well as you have to run it many times to sample this large space here of on the order of 10 to the 39 possible bonding states. What I thought I would do would be to make sort of a toy model. So they call it a toy chemistry model. So mine is a toy model. I've got it started over here, and we're going to start with just 3 particles. So I have not put in any of the actual physics of the scenario yet. All I've got is kind of the basic code for this. So I've got an empty list started here to store all my particles, and initially we're going to give all of them the same radius and mass, so they'll be identical species of particles. And I think I'll keep these values, and then what I'll do when I want to set up different species is I'll just say, 10 times particle radius or 10 times particle mass. So that way everything can scale together nicely. I don't have to worry about multiple values flying around. And then I've got my 3 particles here. So I'm appending to the list 3 spheres. They're all red. They've all got the same radius. And the only reason they'll differ is their position. Oh, I need to change that back to a 1. I changed the wrong vector earlier when I was building this off camera. So I've got these 3 particles. They're going to start at different locations. One will start in the center, one will start to the right, one will start to the left. That is one thing I would like to do differently eventually is, if I can go back to the article, this study was conducted in 1 dimension. Of course, that keeps it nice and simple. That means if you've got 20 particles, that means you've got 20 position coordinates to keep track of. And so they have a little diagram like this. So you imagine, and we'll have this animated within a couple videos, I think. They've got these each individual oscillating like harmonic oscillators, but then bonding and unbonding with each other. So that's pretty cool. But they're only in 1 dimension. I think I'd like to try expanding this to 2 dimensions rather than get a whole bunch of particles and try to recreate what they've got. I think I'd like to expand it, instead of in terms of number of particles, expand it to 2 dimensions. So have some x and y coordinates going on here. For right now, we'll just stick with the x-axis. And then we set all of their masses, we set all of their velocities to 0, we set their initial net forces to 0. So this is the net force on this particular particle in the list. Is it redundant to say particular particle? Because particle kind of conveys particularity. I don't know, something to think about for later. We've got a time step here. This is where we set up the Euler-cromer method. And it's been a while since I reviewed that, and this is a new season, so maybe we'll go over that really briefly. In order to do the Euler-cromer method, you're looking to solve a differential equation using a finite step. So when you write a differential equation, that dt that you write is supposed to be an infinitesimally small value. Well, computers can't handle the infinitesimally small even any better than they can handle the infinitely large. So we set a tiny number, basically small compared to, well, in this case it'll be small compared to the bonding rate that we calculate here, and small compared to the driving frequency that we calculate that we input here. We'll talk more about what that looks like when we go to put it in. But basically, this is the rate at which bonds form between these particles. And so what we do then is we set up a loop, and we're just going to loop this thing forever. I don't have any stopping point in mind just yet. Basically, what we do is we calculate the force on each of the particles. I don't have that in yet. We're going to add in that shortly in today's video. We'll add in 1 single force for this. And then what we do is we loop over the particles. So we do this for every particle. And the first thing we do is we update the particle's velocity. So we update velocity. And what we do with that is we take the old velocity and we add to it the change in velocity. And that's the net force on the particle divided by the particle's mass times the time step. And then we do a similar process to update the position. And that's just the position equals the old position plus the particle's velocity times dt. So these equations come from the definition of the derivative. So velocity is the rate of change of position, so it gives you the little bit of change here. The net force divided by mass is the rate of change of the velocity, so this gives you a little bit of change in velocity here. Now I'm going to run this, and it's not going to do anything terribly exciting. This is just to make sure we don't have any compiler errors or syntax errors. We have 3 particles here. They're all staying in the same location because they have 0 velocity and they have 0 force acting on them. Again, not terribly interesting. So let's start by adding in a force for these folks. Let's take a look here. So there's several pieces to this. I think what I'll do is I'll build this this equation here one piece at a time in these videos, because I'm trying to get back to keeping my videos relatively short. Let's add on the part that we know how to work with, the spring force here. So what we'll need is for each particle in particle list, and it's probably not terribly efficient to loop over both, but I'm going to need to or to make 2 loops like this, but I'm going to need to have a separate loop when it comes to evaluating the bonds between the particles. I think that'll be a little bit cleaner in the long run. So let's see here. We need to have particles force, net force. That's just to emphasize that the sum of all the forces is equal to, so we're only including this part, so I need a negative K0 X. x. So let's see, negative k0 times the particle's position in the x direction. So how far over it is moved in the x direction. So we'll assume that the well is centered at x equals 0. So we're putting them in a harmonic oscillator well, otherwise known as a spring, that is centered at x equals 0. Now I haven't defined this k0 yet, so I better put that up here. Actually, maybe I'll put that, I think I'll put that up here where we set up the initial stuff. So let's say define well properties. And so let's say k0 is equal to, let's make it a nice simple value, 1. All right, so we should get 3 independent springs now. Let's make sure that works. Uh-oh, where did they go? I don't see them. They look like they flew off. Particle net force equals negative k. Yeah, I have those all as zeros, or as I have that as a negative. This k0 equals 1.0. So this is the net force equal to negative k part dot pause dot x. I'm accessing the correct. Oh, that's not being put in as a vector, is it? Oh, well then why not just put in negative k0 part dot pause? There we go. Let's try that. Surprised it didn't give me an error message. Oh well. Okay, so here we go. So these two on the outside are rolling back and forth like this. This one's nice in equilibrium here in the middle. So I've set up my harmonic oscillator potential nicely. That's kind of boring though. Let's make that a little bit more interesting. Let's give them some different initial conditions. So let's give this one, let's displace him off to the side just a little bit. Let's put this one a little bit farther out to the right, and let's put this one a little bit farther in to the left. That'll make it a little more fun to watch for the folks at home. There we go. Okay, cool. So this one is now moving with a much smaller amplitude than these two are. These two have about the same amplitude, but they should get out of, I guess they won't get out of sync because they're all moving with the same frequency, but yeah, I guess they won't get out of sync. Yeah, they're all moving with the same frequency. Cool. So we got this to work. Let's do one more change here just to make things interesting. Let's put this one at negative 0.5. There we go. So we'll watch this one, and then I think we'll call it a day because I think this video is plenty long. Yeah, there we go. Okay, so I've got my 3 particles in a harmonic oscillator potential, and they'll just keep going back and forth all day. When we come back next time, we'll start adding in more of the forces in that list. In the meantime, you can download this basic code, or you can access this basic code, on GlowScript. Play around with it, see what interesting stuff you get. If you'd like to go ahead and move these into 2 dimensions, you can. Thank you so much for watching. I will see you next time. Bye-bye.